In the previous lecture, we have discussed in very detail the LS coupling. You have seen in case of the lighter atoms with multi-optical electron, that is the number of optical electron in those atoms were more than one, how LS coupling takes place. You have seen there are actually three perturbations due to a spin-spin interaction. First of all, the spin angular momenta of different electrons are get added together, and that results in a resultant spin angular momentum, which is denoted by the symbol capital S. Okay, and after that we have considered that there is a residual electrostatic interaction due to which the individual orbital angular momentum vector small l of the individual electrons are added together, and that results in giving the total orbital angular momentum of the atom, which is denoted by the symbol capital L. Okay, and finally there is a spin orbit interaction when L and S both combine to give the resultant angular momentum of the atom, which is denoted by the symbol J. In this way, in three steps, we can understand how LS coupling takes place in an atom with more than one optical electron. Okay. You have seen that due to a spin orbit magnetic interaction, an energy level is characterized either by the values of L and S. Okay, and that energy level is further splitted into the closure energy levels, and the number of those closure energy levels is either 2s plus 1 or 2l plus 1. Okay, the number of energy levels after splitting due to the spin orbit interaction is 2s plus 1 when actually L is greater than S, and it is equal to 2L plus 1 when S is greater than L. All these things we have seen in the previous lecture. Okay. Now these splitted energy levels has actually the particular value of J. It means this 2s plus 1 energy levels in these 2s plus 1 or 12 plus 1 energy levels, each level is characterized by different value of J. Okay. Actually, the group of these different value of J levels forms a fine structure. Okay, that group is called a fine structure. And what will be actually the spacing? Is when you say spacing, it means the energy spacing or the difference in energy between the two lines or two spectral lines of that fine structure. That is called a spacing between the fine structure. And that spacing between the fine structure levels are found by a particular rule, and that very rule is called Landé interval rule. So the prime aim in this lecture is to discuss what is this Landé interval rule, that is how we can determine the energy spacing between the fine structure components after the LS coupling. Okay. Actually, when LS coupling takes place, that is there is an spin orbit interaction, then in the system an interaction energy is developed. Okay, due to this interaction, an interaction energy is developed, and that interaction energy is actually proportional to L dot S. That is, the value of the interaction energy is directly proportional to the scalar product of the orbital angular momentum vector L and the spin angular momentum vector S. So if you denote the interaction energy by the symbol delta ESL, then this delta ESL is proportional to L dot S. Now when we will remove this sign of proportionality, there will be a constant of proportionality, and this constant of proportionality is written by the symbol small a. So you can write the interaction energy after LS coupling is given by delta ESL equal to A times L dot S. Actually, this A is an interaction constant. Okay, this is an interaction constant. Now due to a spin orbit interaction, we get the total angular momentum J of the atom, and this J, which is actually total angular momentum, this is given by the vector sum of L and S. So you can write J equal to L plus S. Now our aim is to find what will be this L dot S, and for this we simply take the scalar self product of this J. So taking the scalar self product we have. Let us see. You have to find J dot J. Okay, this is called a scalar self product. It means you have to find the scalar product of J with J. Now as J is equal to L plus S, so you can write it L plus S dot L plus S. Okay, L plus S dot L plus S. Now you can simplify it. This is L dot L plus S dot S plus L dot S plus S dot L. Okay, S dot L. Now this L plus L, this is in fact L square. S dot S is S square. And as the scalar product is commutative, so this S dot L is equal to L dot S. So the sum of the last two terms, that will be written as 2L dot S. Okay, because S dot L is also equal to L dot S. And this J dot J, this is equal to J square. So from here you can write this 2L dot S is equal to what? This will be J square minus L square minus S square. Okay, and therefore this L dot S, what will be this L dot S? This is 1 over 2 times J square minus L square minus S square. Okay. Now in the previous lecture you have seen that the magnitude of this J, this is equal to what? This is actually J times J plus 1 times H bar. Okay. In fact, if you write like this is mod of J square, this is mod of L square, this is mod of S square, and this is mod of J square, this is mod of L square, this is mod of S square. Why I am writing like this? Because here there will be a confusion if you will write j and also inside the square root you write j, then you will be confused that the j in LHS and j in RHS are same thing. But this is not same thing, because this j is actually magnitude of the total angular momentum vector, and in RHS this j represents the total quantum number. Okay, this is total quantum number, so this is the difference. So write the symbol like this. This is mod j square, mod l square, and mod s square. I am again writing this because it is something going to be, sorry, write like this. This is mod of j square plus mod of, sorry, not plus but minus. This is minus. Okay, this is minus, and minus mod of vector s square. Okay, now mod of j you have studied in the previous lecture that this is equal to square root of j into j plus 1 h bar, and that's why you can write that this mod j square is equal to j times j plus 1 times h bar square, and in this the values of L and S are also written in similar manner, and you have mod of L square. This is what? This is L times L plus 1 times h bar square, and mod of S square, this is S times S plus 1 times h bar square. And so when we will put this value in the above equation where L dot S has been defined, this is, you can see this is 1 over 2. Here there is mod j square, and that will be equal to what? That will be j times j plus 1 times h bar square. But you can see that in all these three terms h bar square is a common factor, so you can take this as a common factor. This is h bar square. Okay, and minus L times L plus 1 minus S times S plus 1 and h bar square. H bar square. Okay, now this h bar square is a universal constant too, and this 1 by 2 is also a constant. So this expression may be equivalently written as L dot S equal to a constant denoted by the symbol capital A times j plus 1 minus L times L plus 1 minus S times S plus 1. Okay, and say this is equation number 2. Okay, this is equation 2, where actually I have written this constant A instead of h bar square over 2. This is just a universal constant. Okay, now as you know, for the various fine structure levels of the Russell-Saunders multiplet, actually the values of L and S are same. they only differ in the value of j. So if you consider two values of j, let us say j equal to j and j equal to j plus 1. So if we consider to find a structure levels having j values, j equal to j and j equal to j plus 1. Actually in LHS j is symbol for j and in RHS it is the value of j. So in fine structure we consider two levels. First one has the j value equal to j and another has j value equal to j plus 1. But as you know, for these two fine structure levels, the value of L and S will be same. L and S will be same. So these two levels have same value. Same values of L and S. L and S will have same value. And therefore, if we now calculate the value of interaction energy, that is when you will find the value of EJ, it means the energy corresponding to the level J equal to J. What will be the value of energy? From this equation, you can see that the energy value will be what? Energy is given by this result. You can see energy given by this equation 1. This equation 1. So EJ, this will be A times L dot S. A times L dot S. Okay. And this will be what? Since L dot S is equal to this much defined in equation 2, so this will be A into A times J into J plus 1 minus L into L plus 1 minus S into S plus 1. Okay. Now, A is a constant and this A, capital A, is also a constant. So the product of these two constants will be actually some another constant. Let us write this another constant by the symbol A prime. So you can write the value of energy EJ equal to A prime times J into J plus 1 minus L into L plus 1 minus S into S plus 1. Okay. Say this is equation 3. Now, in the similar manner, we can find the energy corresponding to the level characterized by the quantum number J plus 1. So again, write the value of energy corresponding to level J plus 1. So E, this is denoted by the symbol E J plus 1. Constant A prime will be same. And instead of j, now we will write j plus 1. So this will be j plus 1 times j plus 1 plus 1, that is j plus 2. Okay. But as I have told you that the values of L and S for these two values of j will be same. So L will remain L and S will remain S. So these terms remain same. This is L into L plus 1 minus S into S plus 1. Okay. Now, let us take the difference of the energy of these two levels. Therefore, the energy difference between two fine structure levels corresponding to, sorry, the page is turned, two levels corresponding to j and j plus 1. This is just the successive two energy levels. Is what will be this difference? This will be Ej plus 1 minus Ej. And what will be this? Ej plus 1. It is defined in this equation 4, you can see, and Ej is defined in equation 3. Since a prime constant is a common factor, so this will be taken as a common factor. And we have to subtract this j plus 1 minus L into L plus 1 minus S into S plus 1 from this. Okay. So this the terms for L and S will cancel out, and in the result you will simply get this is j plus 1 times j plus 2 minus j into j plus 1. Okay. Let us simplify it a little bit. This is a prime times. Now, this product can be written as j into j plus 1, j into j plus 1 and plus 2 into j plus 1. You can write it. Okay. And minus j into j plus 1. Okay. Now this j into j plus 1 will cancel out, and your result is what? Ej plus 1 minus Ej. What will be this? This will be 2a prime times j plus 1. This is the difference of the energy of two fine structure levels characterized by the quantum numbers j and j plus 1. You can see, since this 2a prime is a constant term, therefore you can say that this energy difference Ej plus 1 minus Ej, this is directly proportional to j plus 1. It is directly proportional to j plus 1. So you can see that the energy interval or the energy spacing between the consecutive levels j and j plus 1 of a fine structure multiplet is just proportional to j plus 1. Okay, that is from this law you can easily say that the larger of the two j values are involved. Okay, actually this is known as Landé interval rule. This result obtained here is known as Landé interval rule. Landé interval rule. So you can now easily say what is this Landé interval rule. You can state that according to Landé interval rule, the energy interval between the consecutive levels j and j plus 1 of a fine structure multiplet is directly proportional to j plus 1. Okay, it is directly proportional to j plus 1. So now we will find the we will actually illustrate this interval rule by some particular examples. Okay, now we take some examples. Let us consider three fine structure levels. These three fine structure levels are fine structure levels. Let us consider the three fine structure levels we consider is 3p0, 3p1 and 3p2. 3p0, 3p1 and 3p2. Now, for this 3p0 level, you know this subscript 0 actually represents the value of j. So, for 3p0 level, j is equal to 0. And for this 3p1 level, what is the value of j? This is equal to 1. And 3p2 level, j is equal to 2. Okay, j is equal to 2. And therefore, if you want to find the energy difference between the energy levels 3p0 and 3p1, then we will simply write energy of 3p1 minus energy of 3p0. What will be this? You can see for the two consecutive values of j, the energy difference is given by 2a prime times j plus 1. 2a prime j plus 1. Okay. So what will be this value? This will be here. Let us try to find it in this way. In this way. Actually, we find separately the energy corresponding to these two levels. Now, three this is energy corresponding to 3p1 minus energy corresponding to 3p0. And in this case, what will be the difference of the energy? This will be 2a prime and j plus 1. Okay, and if you consider the value of j is equal to 0, this is 0 plus 1, and this will be 2a prime. Okay, 2a prime. And again, energy of 3p2 minus energy of 3p1 level. This will be 2a prime times 1 plus 1, that is 4a prime. 4a prime. Okay. Then what will be the ratio? The ratio of energy of 3p1 minus energy of 3p0 is to energy of 3p2 minus energy of 3p1. What will be this? This is 2a prime is to 4a prime, and this will be simply 1 is to 2. 1 is to 2. Okay. So the separation between the energy levels, these three energy levels, is of the ratio 1 is to 2. Okay. And yes, you can similarly take some another example. If you consider the another example as three energy levels, let us say 3d1 and 3d2 and 3d3. Okay. In fact, for this level, you can say that j is equal to 1. Actually, this subscript represents the value of j. And for this, j is equal to 2. And for this, j is equal to 3. So now in a short step, you can find what will be the difference of, what will be the ratio of difference of energy. I am just calculating in a short step. Actually, this will be, if j is equal to 1, the energy is equal to 2a prime 1 plus 1. J plus 1 is 2. Now, 2a prime, and now we will take j equal to 2. So 2 plus 2. I am solving this problem in very short step. So this will be in fact 4a prime and is to this is 8a prime. Okay, and therefore this is the in the ratio 1 is to 2. 1 is to 2. Here 4a and sorry, this is actually wrong. No. It is incorrect. In fact, in this case, when you will find the ratio, in fact, j plus 1, you follow a simple trick. J plus 1, here j is 1 and this will be, in fact, j plus 1 and if you will try by this method, then you will get actually the ratio 2 is to 3. 2 is to 3. And this is just a homework for you. You will try. I am not calculating it. Already I have calculated this, and you should try to find the appropriate ratio of the energy separation of these two levels. Okay, thank you. We will see some more videos on this concept in the forthcoming lecture. Okay.